If you're watching this video, hopefully you know all about the fundamental counting principle and how to apply that to basic permutations. But then you might have found out that actually there are more complicated scenarios. What if some items have to be together in a group, like boys and girls have to sit together? What if some items are repeated? For example, if you've got a word that you're mixing up and it's got the same letters in it more than once. Or what if you're arranging a set of items but you actually don't want to select all of the items for your arrangement? So for example, if you're running a race, not everybody can be on the podium. How do we deal with that? Well, today you're going to find out just how to deal with those scenarios. Let's look at grouped items. Bongani is rearranging his spice rack. He decides to put his green spices on the left of the rack, his orange spices in the middle, and his red spices on the right. He has 3 green spices, 4 orange spices, and 2 red spices. In how many ways can Bongani arrange his spice rack? So let's have a look. There's his spice rack, and let's put all his spices on the rack. And we've got there the greens together, the orange together, the red together, just like Bongani wants it. So now what we're going to do is we're going to separate the greens, the oranges, and the reds into their own events. So the greens, oranges, and reds are grouped together there, and rearranging the greens is going to be called event A. Rearranging the orange spices is going to be called event B, and rearranging the red spices is going to be called event C. So how many ways can we arrange the green spices? 3 factorial, because there's 3 of them and they are all unique objects. For B, it's going to be 4 factorial because there are 4 orange spices and they are each a unique object. And for event C, it's going to be 2 factorial, right? So the total number of arrangements is going to be the number of ways that event A can happen times the number of ways event B can happen times the number of ways event C can happen. So it's the fundamental counting principle. And that's going to be equal to 3 factorial times 4 factorial times 2 factorial equals 288. So given that he's grouped the greens, oranges, and reds and put them on a specific place on his spice rack, there are 288 unique combinations within those circumstances. Right, now, what if Bongani decides that it doesn't matter what order the green, orange, and red spices are? So the orange doesn't have to be in the middle, the red doesn't have to be on the right. Now we can rearrange the groups, right? Even though we're keeping red spices together, orange spices together, green spices together. So again, we're going to call arranging the greens event A, arranging the orange event B, and arranging the red event C. And event A can still only happen in 3 factorial ways. Event B will still only happen in 4 factorial ways. And event C can only happen in 2 factorial ways. But there is an extra event here. The 3 spices in their groups now become objects that we can arrange, and arranging the groups is going to be called event D. And because there are 3 groups, we can arrange them in 3 factorial different ways. So now we're thinking about how can we arrange the spices within each of their groups, and how can we arrange each of the groups on the spice rack. So the arrangements is going to be equal to the number of ways you can do A times the number of ways you can do B times the number of ways you can do C times the number of ways you can do D. And it's going to be 3 factorial times 4 factorial times 2 factorial times 3 factorial is 1,728. So Bongani has a lot of ways to choose from. Now, moving on from grouping, we're now going to see how do we deal with repetitions. So that is when in the set of things that you want to arrange, the same thing appears more than once. So let's look at the number of ways we can arrange the word voodoo, right? So if we treat each O as a different letter, right? So the first O, the second O, third one, fourth one, we treat each of them as being a different letter. Then that voodoo there, and the next one there where we swapped the last two O's, and that one there where we swapped the first two O's, those are all considered different arrangements of the word voodoo because each O is unique. So the number of arrangements is simply going to be 6 factorial because in our minds there are 6 unique objects that we're arranging, and that's going to be 720. But what if we treat each O as the same letter? So we're not saying there's a difference between this O and that O over there. Well then, the 3 arrangements of voodoo I showed you there that were considered unique, well, the first one there is just voodoo, and the second one there is just voodoo, and the third one there is just voodoo, and they're all actually exactly the same. So the solution that we had for option A, right, where we had 720 different arrangements, is going to be far too big. It's going to contain a bunch of repetitions, right, that shouldn't be there if we're going to treat each O as the same letter. Now, from that we get a counting rule. The number of ways n objects can be arranged where objects are repeated in the set is n factorial divided by n1 factorial times n2 factorial times n3 factorial times, where n1, n2, and n3 are the number of times an object in the set is repeated. Okay, so that sounds like a mouthful. Let's see by means of an example how on earth do we use this rule. So let's say we're trying to arrange x, x, y, y, z, 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 right? And we want to know how many different unique arrangements are there. So that n there, right, tells us how many objects there are. And if we count, we see that we have 7 objects. So at the top, we place 7 factorial. Then at the bottom, we've got to look at objects that are repeated. So we've got 2 x's, which means we have to have a 2 factorial at the bottom for the x's that repeat twice. The y's repeat twice as well, so we need a 2 factorial at the bottom for the y's. And the z repeats 3 times, so we've got to have a 3 factorial at the bottom there for the z. Now, if there's an item in the set that doesn't repeat, don't worry about putting it at the bottom there. The bottom there is only for the numbers in the set that are repeated, and then the number of ways we can arrange that will be 210. Let's look at a slightly more interesting example. How many arrangements are possible of the word Mississippi, right? So there's Mississippi. The first thing we need to do is count how many letters are there, and we find that there are 11 letters in total. Now we've got to look for repetitions. So we find that there are 4 repetitions of I, then we find that there are 4 repetitions of S, and then we find that there are 2 repetitions of P. So then our arrangements is going to be 11 factorial for the total number of letters divided by 4 factorial times 4 factorial times 2 factorial, where the first 4 factorial is for the repetition of the I's, the second 4 factorial is for the repetition of the S's, and the 2 factorial there is for the repetition of the P's, and we find that there are 34,650 ways in which we can arrange Mississippi. Then we've got to talk about selections. Sometimes the number of objects we intend to arrange are less than the number of objects we have to choose from. So we are then selecting from our set of objects. For example, 10 learners decide to run a race. How many different arrangements of the podium are possible? Right, so there's our podium there. You can be third, second, or first. And there are 3 positions that we get to choose from. So choosing third, we're going to call event A. Choosing the person in second place, we call event B. And choosing the person in first place, we call event C. Now, because there are 10 learners running, when we choose who can be in third place, there are 10 people to choose from. Then, when we choose who can be in second place, there are 9 to choose from because we've already placed somebody in third place. And then when we choose who can be in first place, there are 8 to choose from because 1 is in third place, another one is in second place, and there are 8 people left to choose from. So, if we apply the fundamental counting principle to that, we find that the number of arrangements is 10 times 9 times 8, which is equal to 720. Right, so is there a faster way to do this, right, that maybe includes a rule? So let's look how to derive a rule for this selections thing here. So we said our arrangements is 10 times 9 times 8. And I'm going to write that as 10 times 9 times 8 over 7 times 6 times 5, etc., right? And then, because there are factors at the top and the bottom that's the same, I'm going to just show you that those 7s and stuff actually cancel out so that the two things are equal. It's actually just 10 times 9 times 8. But that 10 times 9 times 8 at the top can be represented as 10 factorial, and that thing at the bottom can be represented as 7 factorial. So we find that our 10 times 9 times 8 is equal to 10 factorial divided by 7 factorial, and that we can write as 10 factorial divided by 10 minus 3 factorial. Okay, so why are we playing these games? Well, if we look at that 10 factorial divided by the 10 minus 3 factorial, that 10 is the 10 learners, right? So that's the number of objects in our set. Not that learners are objects, but anyway. So that is our n. Then that 3 there, that was the 3 places on the podium, right? So that 3 there is the number of selections that we make, and we're going to call that R. So then this formula becomes n factorial divided by n minus r factorial. And that's the formula we're going to use when we have selections. So the counting rule we get from that is the number of ways n objects can be selected in r different ways is n factorial divided by n minus r factorial. Let's see how to apply that. In a class of 20 students, 7 students are picked in order to perform prepared speeches during the lesson. In how many ways can the 7 students be selected? So, the arrangements there is going to be n factorial divided by n minus r factorial, because this is an instance where we have selection. And we've got 20 students, so that's going to be the value of n, and we're picking 7 students, so that's going to be the value of r. So we've got 20 factorial divided by 20 minus 7 factorial, and it's going to be 390,700,800 ways in which we can actually select these 7 students. Okay, let's summarize what we've learned today. We learned how to deal with grouped items, and we saw there were 2 ways. There was the instance where the groups could not be rearranged. And that is when you just find the number of ways that the things can be arranged within each group and then multiply that together. Then we found that sometimes groups can be rearranged. And then we're going to find out how many ways can each of the things in the groups be rearranged. And we're going to see how can the groups be rearranged as well. So there's a fourth thing to consider there if we're thinking back to the spice rack solution, where we were able to now shift the green and red and orange spices to different positions on the rack. Then we spoke about repeated objects, and we found that the number of ways n objects can be arranged where objects are repeated in the set is n factorial divided by n1 factorial times n2 factorial times n3 factorial, where that n1, n2, n3 is the number of times an object is repeated. And you saw that when we did Mississippi and found out how many ways could that be repeated. And then we did selections from a set. And we found that the number of ways n objects can be selected in r different ways is n factorial divided by n minus r factorial. Now, if you want to master something, You've got to do it enough so that it becomes second nature. If Lionel Messi had to think about where the ball was the whole time instead of looking at defenders, he probably wouldn't be that great at soccer. Now, for you, the same thing applies. If you do not practice these 3 scenarios that we've gone over now, you are not going to succeed in mastering it. Good luck.